First of all, I'm going to explain what is a graph in MATLAB. In MATLAB, a graph is a visual representation of data using plots or charts. To be able to create these types of graphs, MATLAB gives us various functions and commands for creating these types of graphs. For example, line plots, scatter plots, bar plots, histograms, and much more kinds of graphs. I'm going to explain this code line by line that generates a 3D plot with 3 lines in different colors representing x, y, and z, where x, y, and z are defined functions of t. So, in the first line of the code, we define the vector t from 1 and incrementing by 0.1 and then ending in 1000. So, the 3 next lines calculate the coordinates of each letter, that each letter is x, y, and z, and all of this for plotting them. The next line is plot 3, x, y, z. So plot 3 is a function used to create a 3D plot. Now, the next 3 lines are used to add labels to the x, y, and z axis respectively. The next line is the legend, and the legend is a line that we put that it adds a legend to the plot and it explains what each line represents. And finally, the line of the title, well, it adds the title to the plot, and in our case, it's called graph 1.
Now we'll present the bisection method. In order to use the bisection method, we have to find the root of a continuous function. To do this, we select an interval where the root may lie. This interval should only have one root, and the endpoints should have opposite signs. Then, once we have this, we calculate the midpoint and evaluate the function at that midpoint. Then we repeat until the midpoint is close to 0. Here we have an example done in MATLAB. As we can see, first we define the function, then we have to define a range. Next, we have to hold the current plot and add subsequent plots. Now we add the grid, the axis, the title, and of the graph. Now we set the initial values for the bisection method. In our case, we have a is equal to 4 and b is equal to 8. Then we set the maximum number of iterations. Now we call the bisection method and then plot the root. And then lastly, we release the plot with hold off.
The Newton-Raphson method, it is also an iterative method for finding the root of an equation or a given function. And the main distinction between this one and the bisection method, although they are similar, a key difference is that while in the bisection method you have an interval, let's say that you think the root is between 0 and 3, and here you just have one initial approximation that you think the value might be in. And another difference is that in here you need to know the derivative of the function. Your function needs to have a derivative, because as we can see in the formula, to get the new value of x, that's our function, our root, we first need to put it, our function evaluated in x, our current x that we're doing, over the derivative of our function evaluated in the x that we're doing. And so how does this work? As we can see in the example, this works by starting at your initial guess, and then it cuts. For example, if you have a function like this, as we can see in the example, it is going to cut with the tangent plane, and it's going to get closer and closer and closer and closer to your actual root. And so how do we find, how we know when we have reached this root? Well, basically it is measured with our convergence criteria, which is that basically we're gonna pick some margin of error between how equal is the last result with the new result. So let's say that when we get our last result was 2.001 and our new result was 2.0001. So at that point we might say, okay, it is good enough. And that will be our root when there's not much difference between two results. and that is the main theory behind the Newton-Raphson method. And now we're gonna go see more in depth the code. Okay, now that we know the theory, we can start on with the code. And so we start with our function and the parameters, which are obviously the function, the equation, our initial guess, the tolerance, which is the convergence, and the max iterations, just so that if we have a lot of iterations, it stops. And so here we first convert them to symbolic functions and then to MATLAB functions. And then it is when we start. So x0 is going to be our initial guess and iterations equals to 0. And so it says, while it does not exceed the max limit of iterations, it is going to keep on going and going. And so here is a formula that we talked about in the past slide, where our new x is going to be our initial x minus the function evaluated in x over the function evaluated in your initial x. And so it is going to keep on doing that until, as we can see there, the difference between your new and old is less than the tolerance level or the convergence level that you had set into it. So when we reach that point, we know that because they are very similar one another, that we have found our root. And so when that happens, we said that, okay, root is equals to x1, new x, and then we just say display the number of iterations that it took and display the approximate root that it was. Okay, and now that we have our function, we can proceed with the rest of the exercises, which they're all the same, just mainly changing the function and your initial guess. So for example, here we have our function, and what we're gonna do is we're gonna plot it first, because we need to plot it first to kind of have an idea of where our initial guess is. And that is a little bit of a disadvantage of this method, that you need to know a little bit about the function in order to have your initial guess right. And so once we do that, we just plot it, and then we call our function of the Newton-Raphson method. And then once we have that, we can also plot the root, and then we just have the result that we can see here, which is our graph, where we have our function and the root, and on top we have as well the iterations that it took and the value of the approximate root. And that will be all for the Newton-Raphson method. Thank you. Okay, so another very important part of this activity was that we have to do an interface, which in the beginning kind of seemed like it was going to be a little bit hard or very long too, but it is actually very easy. So in the app editor in MATLAB, you just drag out the elements that you want. So for example, in here, we have 4 buttons and 1 graph. And so, for example, you can see here in the code that at the beginning, you plug in the functions that you're gonna wanna use. So in my case, I used a plot graph function and my function that I used previously for finding the roots and the iterations. So it is very similar, in which you just need to copy and paste the function that you had previously. And then for each of the activities, it is also very easy. You just practically copy and paste all of their code, except there are some key difference here that, for example, you need to add. For example, we can see that it's plot app dot and then the thing, and other than that, it is basically the same code.
Hello, I am going to explain roots of equations and polynomials. What are roots? The roots of an equation are the values at which the function equals to 0. In simple terms, they're the solutions to the equation. Finding the root is crucial to solve a polynomial, or because those are the real values of every polynomial. Example, if you have an equation where x by square plus 4 equals to 8, the roots of the equation or the roots of the polynomial will be x equals 2. It's what makes that equation right or true. The root function in MATLAB is specifically used for finding the roots of polynomials. It takes a vector of the polynomial coefficients as its input. And how does this function or this word root in MATLAB works? It calculates the eigenvalues of the companion matrix of the polynomial, and this method is efficient and precise for polynomial equations. There are a lot of equations that you could use, like the F0 method or the F0 equations, and you can also use roots, but they are mostly common used for polynomials, and we're going to see them in polynomials here.
Now we're going to see how all this works on code. First, as always, we clear the comments and we start typing clear comments as we clear all close to not have anything mislead there from any previous work. Then we define the function f equals x by 3x. We can see the whole function there. Then we set the range and plot the function x equals -1, then by 0 plus dot 1 equals 5, as we can see there. And then we plot the function, plot we define the function, and we find and display the root. Then the last step, as we can see there, we have to evaluate and plot the roots on the graph. As we plot the graph and we evaluate the polynomial, we have all the comments and how does it work. And then we finalize the plot, and then with the final result, we can see in the graph everything we needed. It is very important to notice that for all this exercise, or to find the root of the polynomial, first we need to define the root. And we have the code to define the root. It's divided by steps. First we define the root, then we try to identify the last coefficient, as we can see there. We then try to find the divisors, divide equals divide, we try to find the divisor, then we initialize the variables, then we test each divisor with each one. When we do a synthetic division in the code, then we check for a root, and then with the root when we got the root, we update the coefficient with a new root. And what is the purpose of this? It's to provide a direct and instructive way to explore polynomial roots using fundamental algebraic techniques like the synthetic division and the rational root theorem, making it more valuable for us in the learning. And this is very helpful because if we don't do this or we don't define the function, it's not going to work later. Now we have here the interface for this root of the polynomial. This interface allows us users to input a polynomial in the form of the coefficients. It helps us to find its roots and then visualize the polynomial and its roots on a graph. Here we have the graph with all the visualized roots, and in the other slide that I'm also in the same video, we have the code to get all this interface. What are all the inputs that we need to do? We need to first put the root finder button function, then we view the graph button function, and this all integrates the user input handling with mathematical operations and enables interactive visualization of polynomial functions and the roots. So we can see the functions and the roots even easier, and it's easier for us with visual elements to work with them. That's the importance of the interface, and it works by the code. First, we need to function the root finder, push tab, then we use text scan, and I will show later how does the code work. Now we're going to analyze the code in the interface and how does it work. Basically, it's divided into parts: the root finder button function and the view graph button function. The root finder button function first part, it starts with the function root finder button push tab event, as we can see here, and this function is called when the root finder button is pressed. Then we have a equals all that, and that is for the polynomial coefficients entered by the user to put in the input field. Then we have a equal a1. That's the column of data from the parsed input that help us to analyze the polynomial coefficients. Then we have roots a, and that's basically to calculate the root of the polynomial divided by the coefficient in a. And then app roots a, that all converts the root to the string and then displays them in the app root so we can see it in their interface. Then we go with the graph function, the part that we see visually, and we have function view graph pushing the function that you can see there. With my hands, I cannot show you clearly, but you can see there, this function is triggered when the view graph function is clicked. When you click that button, it's clicked. Then we can see the function f equals ax by 3, all that, and that defines the polynomial function that is going to be plotted later. Then we hold the current plot, allowing subsequent plot to be overlaid on the existing plot without erasing it, as we can see there. And then we just have the plot, the legend, both of them, and when we stable the grid labels and titles to make the graph informative and easy to read for all the viewers. And that's basically how how does the code works. How do you need to type it? And earlier I showed you why do we work with the interface.